So the topic that Carol asked me to focus on today is phosphorus in dryland P&W soils. And I thought I would structure the talk this way. So I'm going to give just a brief overview of phosphorus in these dryland systems. But then I'm going to segue into a couple of questions that relate to how I think phosphorus is interacting with soil pH now, as we all know pHs have been drifting lower in eastern Washington and even in central Washington as well. And I think that there are some implications with respect to phosphorus availability and maybe some side benefits to use of phosphorus in what are now recently acidified soil. So I'll start with a general overview, and then I'll get to some of these questions, and maybe that will trigger a bit of discussion and certainly some contributions from some of those in the industry, soil testing industry and other. So I think if we remember back to our introductory soil science and plant science, we all know that phosphorus is an essential element, really critical for many plant processes that have to do with how the plant stores and compartmentalizes and moves energy around in the plant, as well as some of the key molecules, the key biomolecules in the plant, so DNA, RNA, cell membranes, and others. And there's a whole laundry list of things that we know are improved or impacted by phosphorus or not if phosphorus is deficient. Everything from certainly yield, root growth, disease resistance, winter hardiness, so on and so forth. And then this last one, tolerance to high aluminum, is something that I'll circle back around to at the end of this talk. We have done some work over the years on phosphorus application in dryland cereal-based systems, wheat in particular. This is winter wheat out in the summer fallow area. We had various trials there where we applied no phosphorus up to reasonably high rates of phosphorus at the high end, 60 pounds of P2O5 per acre in a deep band below the seed row, and got some really phenomenal visual responses and often grain yield responses to phosphorus as well. And I'll note that at this particular site, the initial soil test level was 18 parts per million in a bicarbonator or Olsen test. So normally we would say that at that level of soil test phosphorus, we wouldn't expect to see much of a response. But I think many people experience this, the starter effect of phosphorus, the ability to get improved visual and even final yield responses to phosphorus, even when soil tests indicate levels might otherwise be adequate, are somewhat common. And growers see this when they run out of starter fertilizer phosphorus in the tank or in the box when they're seeding. Sometimes you'll see a stretch of the field where the wheat doesn't look as good, and that is because it didn't get the starter phosphorus application. We also know that phosphorus chemistry in the soil is exceedingly complex, much more complex probably than any other nutrient that we commonly deal with, except maybe some of the micronutrients. Phosphorus chemistry is really strongly influenced or driven by inorganic chemical reactions, things like dissolution and precipitation, minerals that dissolve and reform in soil. A lot of surface reactions that can tie up or absorb phosphorus as well. And most of the phosphorus in soil is in inorganic forms. So mineral forms that control both the availability, solubility, and fate of phosphorus in soil. So really complex chemistry. And again, sort of referring back to diagrams that you might have seen in introductory soil science or plant science, this is one that in a general sense describes the availability of various plant nutrients as a function of pH. So along the bottom of this graphic is soil pH from 4 on the left to 10 on the right. And then the way you interpret this graphic is the width of the bar is related to the availability of the nutrient at that pH. So where the bar is wide, in this case for phosphorus, between pH 6.5 to about 7.5, that indicates phosphorus in the soil is relatively available at that pH. Where the bar gets narrow, availability is limited. doesn't mean that the nutrient isn't there. It's certainly there, but it's in a form or it undergoes reactions that limit the solubility and availability of the nutrient. So for phosphorus, we're looking at this weird dart shape in this graphic. So the complexity of this dart is a reflection of the complex chemistry that occurs with phosphorus across the range of pHs. The bar is wide at high pH. It narrows down at moderately alkaline pH. Gets wide again near pH 7, neutral, and then it gets really narrow at low pH. So stop for a moment and think about, where is your soil pH now, and where is this or where does that fall in terms of the width of this phosphorus bar? Eastern Washington, dryland areas, we're seeing pHs 5.5, 5, sometimes even below 5. So think about that in terms of the graphic and what it tells you about phosphorus availability. And we'll circle back around to that. When we look at the forms of phosphorus in soil, typically at higher pHs, phosphorus chemistry is driven by calcium phosphates, the precipitation and dissolution of minerals that are primarily composed of calcium and phosphate. But at low pH, iron and aluminum phosphates drive solubility and availability of phosphorus, and those tend to predominate or control chemistry of phosphorus at low pH. And again, I'll come back to this here in a few minutes. This relates to a field of science or study called thermodynamics or chemical equilibria. And what thermodynamics says is that if we know the conditions of the system, like pH and the presence of calcium and phosphorus, we can predict what solids are going to form. And that's where a graphic like this comes from, that says at high pH or moderately alkaline pH, 7.5 to 8.5, we predict that calcium phosphates are going to drive phosphorus solubility and availability. And then at the low pH, thermodynamics or chemical equilibria tells us that it's the iron and aluminum phosphates that are going to control solubility and availability of phosphorus. Because phosphorus is a challenge, solubility, availability is a challenge, there's some really great work that was done in the 1970s to develop ways of precisely placing phosphorus in soil close to the root system of a young seedling. And this is some graphics, or a couple of graphics that come from the STEEP, Solutions to Environmental and Economic Problems. If you go back to the original STEEP Conservation Tillage Handbook, the URL is at the bottom. You find some really great foundational work that was done in the 70s with researchers and industry to develop methods, equipment for precision application of fertilizers with the seed, below and to the side of the seed. All of these are intended to enhance the positional availability of phosphorus to a young seedling. And really important for phosphorus, more so maybe than some of the other nutrients. All right, so I'm going to pose a question for the growers in the audience. How much phosphorus do you apply and this focus is a dryland cereal-based system. So how much phosphorus are you putting on an annual basis or throughout a rotation? And think about that relative to these estimates of phosphorus removal per unit of yield. So bushels for wheat and hundredweight for dry legumes and canola. These values, 0.3 pounds of P2O5 to 0.5 pound of P2O5 per bushel of wheat, come from some data that Aaron Esser's been collecting with a small grant to measure the concentration of nutrients in wheat grain and canola seed. So that's the 0.3 number. 0.5 comes from the web, Ag PhD. If you go on and look at nutrient removal apps or websites, they'll give you some of these estimates as well. But think about how much phosphorus you're removing with whatever your yield is for a particular crop in a year or across the rotation. how much you're removing relative to how much you're applying across either the rotation or in a given year. And then think about your input-output balance. So are you taking off more than you're putting on? Or are you in balance? Think about that a little bit. And then think about your soil test results and whether those are going up or down. And the reason I asked that question is when I arrived in Washington a number of years ago, I was often intrigued by the fact that I would hear farmers say, well, I'm putting on 20 pounds of P2O5 per acre and I'm harvesting 100 bushel per acre wheat yield, but my soil tests are either maintaining or going up. So they're removing more phosphorus than they're putting on, but their soil test value is either stable or maybe even increasing. So that is a segue into one of the questions I posed at the beginning, and I want to spend a little bit of time on this question. Is soil acidification promoting phosphorus availability? And does that answer this observation or question that I had based on my initial experiences in Washington? Is there a bright light or at least some positive associated with soil pH decline in Eastern Washington? So let me spend a little bit of time here. Let's go back to this graphic and again, remember that at moderately high pH, 7.5 to 8.5, we know that calcium phosphates drive the solubility and availability of phosphorus. And at low pH, it's iron and aluminum phosphate. And again, think about where we're at now. pHs in the mid to low 5, maybe high 4 range are not uncommon in the top 6 or 12 inches of soil. So this diagram would tell us that iron and aluminum phosphates are sort of driving the availability of phosphorus. Where were we though 30 or 40 years ago? Soils in Eastern Washington were closer to neutral or maybe even slightly alkaline, pH slightly above 7. So we've transitioned, we've gone from neutral to slightly alkaline pH to acidic soils, lower pH. And at the same time, we would predict that the chemistry of phosphorus has changed as well. So we should be shifting from a calcium phosphate-based mineral system to an iron and aluminum phosphate-based mineral system. That's what a graphic like this would predict anyway. So just quickly, a number of years ago, I had a crew in my lab and I sent them out to do some sampling across a transect along Highway 26, east to west, and then also north to south, Highway 195. So they went out and collected samples at regular intervals, east to west and north to south. These samples were a composite from the surface 6 inches of soil in fields along these highway transects. And if you look at the east-west transect along 26, pH at the far left, out in Adams County, western Adams County, 6.6, over in Latah County, 4.3. But along that east-west transect, the average soil pH was 5.2. So again, if you think back to that graphic, it would say that iron and aluminum phosphate should be driving the mineralogy, the phosphorus mineralogy and the chemistry, if you will, at this low pH. So we took those samples back into the lab and we ran a set of analyses, pretty rigorous set of lab procedures that allow you to fractionate or determine the exact types of phosphorus containing minerals that are present in these samples from across this east-west transect. And maybe to our surprise, or though it's sort of consistent with my theory, is we found predominantly calcium phosphate minerals. So 70% of the mineral phosphorus that we found in these soils was still calcium phosphate. Only 2% was iron and aluminum phosphate. So again, think about that in relation to this graphic that tells us at an average pH of in the 5 to 5.5 range that iron and aluminum phosphate should be driving the chemistry. So my theory is that as we've transitioned from neutral to slightly alkaline pH, and have moved to much lower pHs, that we've temporarily increased the solubility and availability of phosphorus as the calcium phosphate minerals dissolve on their way to forming more iron and aluminum phosphate. And the reason I say this is that that graphic that shows us nutrient availability as a function of pH is based on thermodynamics, and thermodynamics tells us where we're headed, what should be present in terms of the minerals given the conditions like pH. But kinetics controls the rate of those reactions, how quickly calcium phosphate's going to dissolve and reform or reprecipitate as aluminum and iron phosphates. And my theory is that we're in this transition where ultimately we will see much higher levels of iron and aluminum phosphate, but the kinetics are such that it's taking us a while, decades, if you will, to get there. And then in the last few minutes here, I want to circle back around to my second question. And this is sort of a flip of the issue of phosphorus availability being controlled or reduced by iron and aluminum. I want to ask the question, are there hidden benefits of the use of phosphorus beyond crop nutrition and in particular in our now recently acidified soils? So again, we'll go back to this graphic and focus here on the low pH end, where the dart for phosphorus, if you will, gets very pointed or very narrow in terms of the width of that bar. And that would tell us that iron and aluminum phosphates are controlling phosphorus solubility and availability at low pH. But there's another way that we could flip this or look at this. Here's a slightly different graphic that tries to show the same relationships. Nutrient availability is a function of pH. But this one does include aluminum and iron on the graphic and calcium here on the right. And the reason I like this graphic is it sort of indicates that there are teeth, if you will, on aluminum and iron that are eating away at or chewing on phosphorus, implying that iron and aluminum are consuming or precipitating or tying up phosphorus at low pH, and calcium over here on the right at high pH. So if we flip this from a aluminum reducing phosphorus availability perspective to, does then phosphorus tie up aluminum? And is there some benefit associated with the use of phosphorus in low pH soils that have high levels of exchangeable aluminum that might be toxic to the plants? And if you poke around a little bit, this happens to be a publication from Oklahoma State University, but you can find similar publications from University of Kentucky, Kansas State, other states who have acid soils and grow cereal crops. So the title of this publication is Phosphorus Fertilizer Protects Roots from Aluminum Toxicity in Acid Oklahoma Soils. You can find this online, and it's a bit surreal when you read this. It talks about soils in the state of Oklahoma becoming more acid, pH is declining, that it's been a challenge for cereal production. And it's also been a challenge for them to find economical sources of lime to treat low pH or acid soil. So in this yellow highlighted area, you see the statement, to maintain productivity in the short term, producers have been using in-furrow band applying phosphorus fertilizer to alleviate the impact of aluminum toxicity. And they reference this guide over here from the 1980s based on research in the 1970s, where they were using seed banded phosphorus applications in low of lime applications to try to, in the short term anyway, address aluminum toxicity, and it worked. There are a couple of graphs in this publication. This is one here that in Oklahoma, they do a lot of winter wheat grazing in the fall and over winter. So this is winter wheat as a forage. And then They take winter wheat often onto grain, but you can see the response to seed placed phosphorus across a range of soil pHs and also wheat cultivars. There are some other references and figures in this publication where they compare seed placed phosphorus with lime applications and show that in many cases the use of phosphorus was more effective than the use of lime in addressing aluminum toxicity in these systems. So back to that original question, are we getting some other benefit beyond plant nutrition to the use of phosphorus, and in particular seed-placed phosphorus, where it's protecting the wheat seedling or the cereal seedling as it initially germinates and begins to grow. I think the prospect is probably good. There is, I think, likely some benefit that we're seeing there. All right.